never told me that my whole life.
Bet you have good handwriting.
Wow.
He's just trying to be great.
Thanks for that 92 on the lab.
That's moving up. I'm changing it right now. All right, let's, any questions first? I'll take any questions first on anything. What we did yesterday, we did the double integral as a means to finding mass of a lamina of varying density. Did you get those notes? I have the notes in my office. I'll have to give you those notes. So we did that yesterday. We did that right triangle. We saw that if we made the density function proportional to x, a kx, what it did, it moved the centroid down the median heading towards the point 60. Okay? And I believe your lab deals with that very issue, so you can do some stuff with the lab on that and see what happens, have Mathematica do it for you. It's really good. Any questions at all? Dylan, you're far away. I know, but all right, go ahead. Question.
Yeah.
Almost got a question.
Another double integral.
Double integral, let's do it.
0 to 2 for the first one, and then y to 2y for the second one.
Say it again.
Y to 2y.
Well, y to 2y, yeah?
And then the function is 10 plus 4x squared
I'm sorry, say it again.
plus 4x squared plus 2y squared dx dy.
Okay, let's take a look at this. This is the problem to evaluate this double integral. And let's just think about what we're doing here. What we're doing here, one of two interpretations we have of this double integral, what it's doing. One interpretation is we're finding a volume underneath this surface, z equals 10 plus 2 plus 4x squared plus 2y squared, over this region. And the region is this here. Let's take a look at this region in the xy plane. The x's are going to y to 2y. X equals 2y, which is this. This is x equals y, and this is x equals 2y. Okay? That's what the x limits are. The y limits are 0 to 2. 0 to 2. This is y equals 2, 0. So we're finding the volume underneath this surface over that triangular region. Okay? Over that triangular region.
So you take two essentially equations, intersect them, and the area between which they intersect to your endpoints and your x-coordinates are going to be what defines your volume.
Yeah, underneath that surface. Yes. Yes. Yeah. Yeah. These give you boundaries in the xy plane. Exactly what you said. X is going to go from y, that's this, to x equals 2y, this, and the y's are going to go from 0, that's the x-axis, to 2. And this is going to intersect here somewhere.
Just like in Calc 2 with normal integral, but now you're adding another.
Yes, that's true. Or, another way to interpret this is what we have here is this lamina in the xy plane with a density function that's 10 plus 4x squared plus 2y squared. And we're finding the mass of that lamina. It's another interpretation of this double integral. So each point at 0, 0, we got a density function of 10. At this point here, say where x is equal to y and y is, this is point 2, 2. Okay. We have a density function that's 10 plus 4 times 2 squared plus 2 times 2 squared. That's the density at that point. So we have a lamina that has constantly varying density. Okay? Yes, Brandon?
So lamina is just that two-dimensional.
Yes, that is the lamina right here, this object. And let us evaluate it. Let's do it. 0 to 2. We're going to integrate with respect to x. We're going to get 10x, 4x cubed over 3, a 2xy squared. Y is going to go from y to 2y. I mean, the x is going to go from y to 2y, I'm sorry. The x is going from y to 2y. Substitute in the 2y here, we're going to get 20y plus 4 times this cubed, which is 8y cubed. So we're going to get 32y cubed over 3. Oh boy. Put in the 2y here, we're going to get a 4y cubed minus, now substitute in y, 10y, minus 4y cubed over 3 minus 2y cubed. I hope something happens that's nice here. Some kind of simplifications. Something. Let's see what we have on the y's. I have 10y. Oh, that's pretty good. Now, I've got 32y cubed over 3 minus 4 of them. That's 28y cubed over 3. Then I have 4 minus 2. I have 2 more y cubes over 2 more y cubes. 4 minus 2. Okay. Well, I'll tell you what. I'm going to combine these guys. I'm going to multiply by 3 over 3 to get 6. I'll have 10y plus 34y cubed over 3. Gee, the heck? Okay, and now let's integrate this with respect to y. 10y squared over 2. 34y to the 4th over 4 gives me 17y to the 4th over 6 when you simplify. Okay. And I'm going from 0 to 2. All right, substitute in 2. 2 squared is 4, you get 20 plus, oh boy, 2 to the 4th, that's 16 over 6, that's 8 thirds. 8 times 17 is 136. Okay. Over 3. I think that looks good. 856, yeah, that looks good. And now multiply by 3 over 3 to give you 60, 196 over 3. And I believe that should be correct. It is correct.
I don't know, but
Oh,
it's a lot different than when I got.
A student that really wanted to be in this class would say, yes, Burns, that is correct. So, is this correct?
Yes, George.
Good answer, Omar. I'm sorry. I shouldn't have done that too. All right. Any questions on that? Ready? Any other questions at all? Let's move on. Let's go on. What the heck? Here we go. Let's do a triple integral. Ooh, here's what we've got.
I'm scared. Yeah, me too.
Let's take a look. Let's take a look at a triple integral and when we would use such a thing. Let's take a look at this. Let's suppose we have two surfaces in space. Let's take z equals 8 minus x squared minus y squared. And let's take another paraboloid, this one here. Let's take z equals x squared plus y squared. Those two paraboloids will intersect. And what we'll have is an egg-shaped solid. Okay, egg-shaped solid. Let's further suppose that we have a density function. That's proportional to z. In other words, as we move up off the XY plane, this thing is getting denser all the time. Yes? Oh, sorry.
Is that a P or a row?
That is a row. That is a row. Density function, yeah, always is row. Okay. So, here's the problem. We've got one problem is to find the mass. Okay? We're going to find the mass. A second problem is to find the center of mass. X bar, Y bar, Z bar. Okay. Well, let's just take a look at the second question first. Can someone give me 2/3 of the answer to question number 2?
It's going to be X equals 0 and Y is 0.
And Y is 0 as well. Yeah, 0, 0, something. Now, that something, let's see what we have about that Z. Well, first of all, let's take the intersection of these two objects here. The intersection of those two objects is going to be this. We're going to set these two equal to each other to find how they intersect. Add the x squared, add the y squared. Divide by 2, we get x squared plus y squared equals 4. That's their intersection. We have a circle of radius 4. We're going to take this circle and bring it down to the xy plane. Okay, so we're taking this circle right here and bringing it down to the xy plane. Okay, now here's the question. And what's the z coordinate? What is this point right here? This point right here is going to be, what is z at this, where they intersect? That's going to be 4. It's going to be right in the middle. 0, 0, 4. Okay? Here's my question to you. Will z bar be greater than, equal to, or less than 4? It'll be greater. Because it gets denser as we move up off the xy plane. So z bar will be greater than 4. I'm not sure how much greater than 4, but certainly greater than 4. And obviously less than 8. Somewhere in there. Somewhere. Okay? Okay, that's the problem we have to do. So let's do it. Everybody have this? Okay, well, I can do the mass right on here. Let's find the mass. To find the mass, what we're going to do is divide this solid up into cubes, little cubes. We're going to slice it in 3 different directions, okay? This way, and that way. We're going to slice these up into little cubes, and I'm going to take one of those little cubes in here. Let's just take one of these guys. Okay, 1 cube. The mass of that 1 cube, okay, and I'm going to call it the ith cube, is approximately equal to the volume of that cube times a density function at anywhere in that cube, as long as you're consistent from cube to cube. In other words, you could take the lower left vertex or whatever, and that's the volume of that 1 cube. I mean, that's the mass of that 1 cube. The mass of the entire solid is the sum of all these masses. And that mass would be equal to the limit, as n goes to infinity, of the sum of all these. Now, I'm using one I here, an index I. It could be I, J, and K, because they don't have to be all the same I. But I think for simplicity's sake, I'm just going to call it I for each of them. The point is, what we have here is a Riemann sum in terms of x, y's, and z's, okay? And how do you evaluate that Riemann sum in terms of x, y, and z? That's a triple integral. And that's exactly what that is. That is going to be the triple integral, okay, of our density function. And the usual is dz, dy, dx. The z's are going to go from one function of x and y to another. Can you guys see? Am I on the board there? Yes, I am. Barely, but I'm there. The y's are going to go from one function of x to another. And the x's are going to go from one constant to another. In general, to find the mass of this solid in space bounded by these two surfaces, f1 xy and f2 xy, with a density function, okay, of rho x, y, z, this is what you use, okay? That triple integral will give us the mass. Yes?
So when we started this chapter, you said you like double integrals because of what we ended up doing with them?
Yeah, with the triangle, yeah.
Oh, okay. I was going to ask what you thought was cool about double integrals because it seems like this is a much similar process.
This process is similar, but it's the double integral with that right triangle where the centroid of that lamina varying density moves right down the medians.
Yeah.
And it's really cool. If you do it in Mathematica, and you can see it moving down and going this way and moving up the other one. And then when you vary it, you can see it goes along the path you would think it would go. It's just amazing stuff. And when you take that limit as n goes to infinity, because you have a density function kx to the end, bam, that's what the limit is, 6, 0. It goes right there. I think that is it's just so cool that the math and your intuition agree. But contradictory to that, though, is some of the coolest problems in math are the ones that are not intuitive. They're anti-intuitive. They're counterintuitive, where you think this should be it, but it happens to be something else. But in other words, it's all good. You know what I mean? All right, so anyhow.
I want to make sure it didn't get more complicated than we had already covered.
No, we're about there. The most complicated. This problem is going to be very complicated in rectangular coordinates. We're going to have to go to cylindrical because we get this circular region here. Okay, we're going to have to go cylindrical, and then what we're going to do on Monday when we get back from Thanksgiving break there is we're going to do spherical coordinates. But it turns out the spherical coordinates, which look complicated, more complicated than either of these two, turns out to be pretty simple because you use them only when you're dealing with spheres. And when you're dealing with spheres, the equation for that sphere in spherical coordinates is the rho is equal to a constant, the constant being the radius of the sphere. So it turns out to be pretty simple. That's pretty cool. Okay, so here's the mass of this object in general. I'll tell you what I want to do. We're going to get back to this problem in a second. But what I want to do, I'll do the problem right now. Let's do the mass of this right now. And then what we're going to have to do, in order to calculate the center of mass, we're going to have to calculate mass times a distance from each of the coordinate planes. Okay? In order to get that center of mass, just like we had to do the other day with the lamina in 2 space, we have to do the same kind of thing. We have to calculate the moment generated by this about each of the coordinate planes. All right, so we need a mass times a distance. All right, but let's do the mass first. So let's set up the triple integral that will give us the mass of this object. You ready? Let's do it. Okay. So the mass of this particular object is the triple integral of our density function. Okay. Dz, dy, dx. Now, what about the z limits? Where are we going on our z limits?
squared plus y squared to a minus x squared minus y squared.
Perfect. Bottom to top on the surfaces. Okay? That's what you want on the z limits. Z goes from the bottom function, bottom surface, up to the top surface. Here, let me redraw the circle again. Hold on. This is 2. These are 2's. Sorry, my bad. Okay, x squared plus y squared indeed is equal to 4, but the radius is equal to 2. Okay? Sorry. Okay. What are my y limits here?
2 to something.
My y limits are what? Well, I'll tell you what. We got symmetry all over the... Well, let's go not 2 to negative 2 on the y's.
Yeah.
No, well, if you want to just do the quarter here, let's do this quarter part. Let's do this. It starts at 0, all right, but it doesn't end at 2. If you're going to end the y's at 2, you're saying it ends at the straight line 2, a constant 2. It doesn't. The top part of the y's are this function. And what is that function? Yeah, that's it.
Oh, I thought we were converting it already.
We need square root of...
Negative x squared plus 4.
What's that?
Negative x squared plus 4.
Yeah, 4 minus x squared. I'm going to write it that way, but you're right.
Yeah.
You're right. Okay. And my x limits are going to be 0 to 2. Now, there's a problem. Okay, the problem here is the square root of 4 minus x squared is a problem. When we do the integral out here, whoa, we got a problem here too, because when you do this, you're going to have these problems do get nasty, but they're not complicated nasty. They're algebraic nasty. Okay, is what happens. You get kz squared over 2. You substitute in this for z. You're going to have to square this. You're going to have to square this. Subtract the 2, and then integrate. So that's the z. And then when you integrate that with respect to y, you're going to have to substitute these in for the y's, and then you're going to have to integrate with respect to x, and you're going to have these square roots in there. And that's not good. You can do them with a trig substitution. Let x equal 2 sine theta, and they're doable. But you don't want to do that if you can avoid it. The way to do any of these problems are when circular bases, okay, circular regions in the xy plane, as long as we're not talking about spheres, and we don't have spheres here, if we got circular regions, we want to go to cylindrical coordinates always. So let's set it up with cylindrical. We still have a kz, and now we're going to have a dz, but instead of dy dx, what are we going to have? And what else besides, and you need one other thing here. R. Who said that? Wow. Okay. You need an r d theta. Plays the same role as dy dx. It's the area of one of those little pieces. Okay, and that's what we did the other day. We proved that the area of one of those little pieces, okay, is r delta theta, which becomes the r d theta. Okay, with the x's and y's, it's delta x and delta y, which becomes dx dy. So now, what are my limits here for z? X squared plus y squared is what? R squared. And 8 minus x squared minus y squared is?
8 minus?
Yes, very nice. Very nice. What about r? Where's r going? 0 to 2. Now we do have a constant there because the equation here is r equals 2. And where are my thetas going? 0 to pi over 2. Very nice.
You have to multiply this by 4.
Yeah, that's a good idea. Let's multiply this by 4 to get the actual answer. Good call. Good call. Okay, let's do it. Let's calculate the mass. What the heck? Liam.
Can we just like go through the x squared plus y squared conversion to r real quick?
Say that again? X squared plus y squared is r squared?
Yeah, can we just do that out real quick?
Yeah, sure.
Yeah, I answered that, I'm still wondering.
I can probably find it in my notes where there's so many pages.
No problem. Well, we can do it right here. Watch this. I'll show you. Okay.
Oh, that.
Guess what? This is it.
Yep.
And for minus would just be another quadrant.
Say that again?
It was, well, no, for x squared minus y squared,
That's nothing. That's bad news.
that's not what that is.
Oh, because it's not x squared minus y squared. It's minus x squared plus y squared in parentheses,
Which is r squared.
which is r squared. Yes.
Okay.
Okay.
Thanks.
No problem. All right, 0 to 2. All right, let's do this integral. We can take the k out front too, okay? And we have zr, and the integral of zr is z squared over 2, okay? R, the z's are going to go from r squared to 8 minus r squared, and then we're going to have a dr d theta. I'm going to take this 2 out front to get 2k. 0 to pi over 2. 0 to 2. I took the 2 out front. I'm going to replace z with 8 minus r squared. So I'm going to have 8 minus r squared squared times r minus r squared squared out of the 4th times an r. All right, is that what I replaced the z with an r squared, so it becomes r to the 4th times this r. I'm going to have a 2k, 0 to pi over 2, 0 to 2. Now when I multiply this out, I'm going to have a 64r minus 16 r squared times r, so minus 16 r cubed.
We could do U substitution, right? Over there.
Say that again?
U substitution.
Oh, if I integrate this without doing it all out?
And then you have the r there.
Wow, that's not a bad idea.
And then just doing a second.
That would mean me scribbling this out and admitting to a Burns mistake, of course. That's good. Well, it is. I should have seen that. That was a good suggestion. I'm going to do it. I'm going to because I'm going to have to integrate this, and I don't need to multiply it out. I'm going to do what he said.
That's awful.
I know it. Just put it down in your notes. Burns mistake.
Sell it to a museum.
Yeah, that's true. Very rare, very rare. So you get 2k, 0 to pi over 2, and now I'm going to integrate this without multiplying it out. Okay, this is what I'm doing right now. So I've got a u to the n form, where u is 8 minus r squared. The du is a negative 2r dr. So I'm going to have to multiply by negative 2 and negative 1/2. So I'm going to get a negative 1/2, 8 minus r squared cubed over 3. Okay, that's this one right here. Minus, now this is r to the 5th, and that's r to the 6th over 6, and I'm going from 0 to 2. Okay, so check that out. That looks pretty good, though. Nice. That was a good suggestion. So that's 2k, 0 to pi over 2. Substitute in 2. So I'm going to get 4 cubed over 3. Now I'll write it out. It's 4 cubed over 3. Okay. Minus 2 to the 6 is 64 over 6, 32 thirds. Minus, plus, substitute in 0. I've got 8 cubed over 6, 2 times 3. All right? And then a 0 here finally. Okay, so I think this is what I have right here. So I substituted in 2, got that. Substituted in 2, got that. Substitute minus plus this. I think that's okay. This mess, can anybody simplify this for me?
Yeah.
What does this simplify to?
Like do it in my head or anything.
I could do it in my head. I should just do it.
The
Nah.
4 cubed would be another, would be 32 as well, wouldn't it?
4 cubed is 64 over 2 is 32. Oh, but they're both minus. Oh. All right, so well, let me do it out. 0 to pi over 2. Okay. This is 4 cubed, 64 over 2 is 32, like Dan said, but it's 2 minus, so I get minus 64
It's
thirds.
64.
I got 64 as well.
Oh, plus the 8 cubed over 6? And that gives me 64, this mess?
Yeah.
Hey, cool. So, did you multiply by 2k yet?
No.
Okay, so you get 64 out of this, so you get 128k. Okay. 0 to pi over 2, d theta. Wow, that's 128k. 128k. I think that was my,
We're gonna be rich.
no, that was my Radio Shack computer. I think it was a 128k machine in 1980-ish or something, whatever it had. That Radio Shack,
Clock speed or
what's that?
is that clock speed or how much memory? it
That's how much memory it had. That was the memory it had. 128k.
Entire paragraph.
Wow, that was cool stuff. Oh, we had floppy disks. Yeah,
Yeah.
we had a tape recorder on that one actually.
Wow.
A little tape recorder.
And an ashtray?
That was cool stuff. Times pi over 2. It seems to me we're going to end up with 64k pi.
That is what mathematics says.
It is. Yes. Thank you, Dan. All right, so that's the mass of this object, this solid bounded by these two paraboloids with this varying density, where it's getting denser and denser. Now, what we now have to do is calculate the moment that this thing generates from the xy plane. Okay? So let's go to that problem. Here we go. Everybody else up with this? So here's what we got. Watch this. Moment from the xy plane is equal to, I'm going to do this in general first, and then we'll do it for this specific problem. Okay? Is equal to the triple integral, okay, of our density function
Burns, we were way past that 12:30 mark.
Oh, we are. That's true. I lied. Oh, man. All right, that's true. Density function. Now, we got a density function times the delta x, delta y, delta z, which gave us a mass of that cube. But what we need to know is what the moment this cube is generating about the xy plane. So we're going to have to multiply this mass by a distance. And what distance do we need from the xy plane? Z. Good job. So we need to multiply by z.
He's never in this office.
I knew z was good for something, though. Here you, all right, there you go.
Too bad he's not like walking by her. Yeah, he'll see it on YouTube.
That's true. It's all recorded. Oh, man, I'm cooked. All right, so that's the moment from the xy plane, where, again, the limits of integration are one surface to another, just like we had before. The difference is we multiply by z, which is that distance. So let's do it, okay? Our moment from the xy plane. And, of course, if we needed the moment from the xz plane, we'd multiply by y, and moment from the yz plane, we'd multiply by x. But we don't need those, because we know those answers are zeros. Yes?
So if we needed the moment from x or y, would
or would we convert it to terms with x, y into a double integral?
Started off as a triple integral. Some of these problems will resolve into double integrals, though. That is true. But this one here, we're going to need the triple integral to begin with. But some of them do resolve into double integrals. Depends on the problem itself.
For the x and y, sometimes you do need a triple.
Yes.
Okay.
Yeah. So, here we go. Let's do it. Moment from the xy plane, triple integral, z. Our density function was a kz. We have a dz, dy, dx. We had our z's go from the bottom, x squared plus y squared, to the top. We had our y's go from, and we need a 4 here. We had our y's go from 0 to the square root of 4 minus x squared. And we had our x's going from 0 to 2. Okay? And that's what we had last time. The only difference between this and what we did last time is the additional z that we have there for the distance. We're not going to do this integral. We're going to change it to cylindrical. So here we go. 0 to 2. 0 to, and we had on this one here, now this is 0 to pi over 2 rather. Okay. And this is 0 to 2. And this is r squared, 8 minus r squared. We have a k, I'm going to take out front. We have a z squared. And we have an r dz, dr, d theta. Okay, does that look about right? The difference is we have a z squared now. Everything else is the same. This is what we have. Okay? Okay, you ready? Let's do it. Here we go. 4k. 0 to pi over 2. 0 to 2. Integrate with respect to z. Z cubed r over 3. I'm going to take the 3 out front. I'm going to go from r squared to 8 minus r squared. Dr d theta. So 4k over 3, integral 0 to pi over 2. Integral from 0 to 2. Substitute in for z, 8 minus r squared. Oh, we definitely want to do the u substitution thing here because this is cubed r minus z cubed, substitute r squared for it. R squared, that's r to the 7th now. It's r to the 6th after we cube this and multiply by r. Okay? Holy moly. Remember what we're looking for. We're looking for an answer ultimately where z bar is something a bit greater than 4 because it raises above the center, but certainly less than 8. It's got to be in there somewhere. Okay? If we don't get an answer in there somewhere, we made a mistake. So 4k over 3, 0 to pi over 2.
Is that a minus r squared?
That's a minus r squared here, yes.
I mean in the 8 next to the dr.
That's a minus r to the 7th. Yeah, it's r to the 7th. Because we end up having to substitute r squared in for z cubed, and that gives us an r to the 6th power times r. Okay, so I'm going to do this as a u to the n form, where u is equal to 8 minus r squared. The du is a negative 2r dr, like we did last time. Multiply by negative 2 and negative 1/2. And end up with 8 minus r squared to the 4th over 4 minus r to the 8th over 8 from 0 to 2.
So could you take out a negative 1/2, 1/4?
I can take out a negative 1/8. That is very true. I have a negative 1/8 here, and I have a minus 8 here. I can take both of those out. Okay, so I'm going to take 4k over 3, and I'm going to take a negative 1/8 out. And I'm going to be left with And 8 minus r squared to the 4th minus r to the 8th. From 0 to 2.
This is almost a 3-page problem.
What's that? Yeah, this is a problem and a half, that's for sure. What's what?
The limit there?
0 to pi over 2. Yep.
Shouldn't that be positive or to the 8? Because you took negative sign out.
Thank you. Thank you. I took the negative 1/8 out, that becomes a plus. Thank you.
Yeah, just go erase his grades.
Okay, you guys ready? This, substitute in the 2, I'm going to get a negative k over 6, okay, 0 to pi over 2. Am I still on the board there? Yeah, a little bit. Okay, substitute in 2, squared 4, 4 to the 4th, plus 2 to the 8th, which is 4 to the 4th, minus, substitute in 0, to get 8 to the 4th, and a substitute in 0 here to get 0. So, d theta. All right, here's what I need from someone. 4 to the 4th plus another one. That's 2 4 to the 4th minus an 8 to the 4th. What the heck do I get there?
We could take 4 to the 4th common, right?
Say that again?
4 to the 4th common, like, take it out.
I could do that, and this is 4 to the 4th times 2 to the 4th. I could take a 4 to the 4th out, and I have
2 minus 2 to the 4th.
1 plus 1, a 2 minus 2 to the 4th, and a 2 minus 2 to the 4th is a negative 14 or something, but negative 14 times the 4th, I need someone to do it out.
Negative 3,584. Yeah, that's what I got.
What? Negative 3,000 what?
584.
584? Ugh, I'm not sure if I like that. Okay, there's that. Ugh. Take it out front, at least it's negative, that was good. So is this divisible by 6,
No.
12? No, it's divisible by 2. So I'm going to take it out front. I'm going to get a k, 3, and divide that by 2, so I get 1792, I think. It's going to be positive because I take it out front. And I have this.
Nice try.
And now I have 1792k over 3 theta, 0 to pi over 2. So I've got 1792k over 3 times pi over 2. Divided by 2 to give me 896k pi over 3. That is the moment from the xy plane.
Can you go back to the previous page?
Yeah.
Go back to the current page.
Where do we start this problem? Holy mackerel. We're almost there. We're almost there.
We got
Okay.
like 3 of these to do on the test, right?
Actually, it's 20. One for each multiple choice. Yeah. Yeah. So, carve out a bit of time in your schedule, like 2 weeks, and you can do it. All right. So here's what I got. X bar, Y bar, Z bar is equal to 0, 0. Z bar is the moment from the XY plane divided by the mass. We get 0, 0, 896k pi over 3 divided by the mass, which I have somewhere, 64k pi. That was my mass. I get 0, 0, k's cancel, pi's cancel. I get 896 over 3, which is 192, right? And what'd you get?
14 by 3.
14 over 3?
I agree.
Oh, if you guys agree, Who am I to argue with that? And guess what that is? The answer is 4 2/3, which means what we've done by that density function, increasing density as we get closer to the top, move that center of mass from the 0, 0, 4 point to the 0, 0, 4 2/3 point, moved it up just a bit, okay? Which is enough to get it off that midpoint. And we are done. So, here's what you should be doing. That worked out great, huh? That was cool. What you should be doing is tomorrow, I'm going to be here. Anybody needs help? You need help doing problems? Help doing a lab? I'll be here. Okay?
Help doing all the labs.
I don't care, whatever it is, I'll be here. And otherwise, I'm not doing anything good. Okay? Have a great Thanksgiving. See,
You're saying that now.
lab number 5 is due, when'd you have the test?
Whoa. 5 labs?
Oh, the test is next Thursday, the lab is due a week from Friday, at midnight.
Let's not get ahead of ourselves.
Yeah. Have a great Thanksgiving.
We'll have to
See you sometime.
Tomorrow.
What a problem. Holy mackerel.
I'm gonna go.